on this question, we have an indefinite integral, and that integral is sine of 5x cosine of 5x dx. So when you have a problem, well, generally most integration problems, you're going to try to use what's called the substitution method. And the substitution method allows you to make a substitution to simplify what the integral looks like so that you can choose the correct antiderivative to work the problem out, the correct antiderivative rule to work the problem out. Now, especially when you're learning, you're not super familiar with all the integration rules, and you're not sure which substitution is going to work. So let me try a substitution that I know is not going to work and maybe talk about why we know that. So the first clue that most professors tell you is to choose something for you that is inside. So we have 5x on the inside of both sine and cosine, so that might be your first guess for using this u substitution. So let me choose u to be 5x. When you make your variable change, when you make your substitution, you have to change what variable you're calculating the antiderivative with respect to. So we need to calculate the derivative of u with respect to x, and that's going to be 5, so that we can make that variable change for the dx as well. So I'm going to make the substitution that I have so far. We're going to substitute for dx, and we're going to substitute for the u being 5x. Let me rearrange the second part here. We'll have du equals 5 dx. And solving for dx, we have dx equals du over 5. So I'll make the substitution, and that will give us sine of u cosine u du over 5. And we can factor out the 1/5. That gives us the integral of sine u cosine u du. Now, the substitution that we've done is done correctly, but it hasn't got us any closer to which antiderivative rule we should use to apply this integral. We have rules like integral of sine u du is negative cosine u plus c. And we have integration rules or antiderivative rules like cosine u du is sine of u plus c. But the function that we're trying to find the antiderivative of is sine of u times cosine u. And that's not what either of these rules state. It's just sine on its own, cosine on its own. So although the substitution that we've made here is correct, it didn't help us in finding the correct antiderivative rule to use. So let's try a different substitution. So I'm going to try to choose cosine as my u. So another tip that a lot of professors will give for choosing what u should be is you want to choose something for u where you have the derivative of that thing in your integrand. So I know that the derivative of cosine is negative sine. So that might work with my substitution. So let's choose u equal to cosine of 5x. When we calculate the derivative of u with respect to x, the derivative of cosine is negative sine of 5x. And you can see that the derivative of cosine, which is sine, is in our expression. So this might be a really good choice for us. Let's go ahead and rearrange solving for dx because I'd like to substitute for dx. That would give du equals negative sine of 5x dx, and I'll divide by negative sine of 5x on both sides. So that will give dx equals du. And I apologize, I just realized I made a mistake. So going back to our derivative here at this step, I've forgotten to use the chain rule. The derivative of cosine is negative sine, but we've got 5x inside there, so we need to chain and multiply by 5. So this is going to have a times 5, and we're dividing by that 5 as well, and dividing by that 5 as well here. So let's make this substitution. We're going to substitute all of this for dx, and we're also going to substitute in for cosine of 5x u, and let's see what shakes out. We have the integral of sine of 5x times u times dx. Dx is du over negative sine of 5x times 5. Now, luckily, this substitution is going to work because when we make a variable change, like we've done here, we're changing from x to u. We need to completely change variables. We don't want to leave any of the other variables still in our expression. So you can see that we still have x's here. But the reason why I said luckily is our sine of 5x and sine of 5x is going to cancel with that substitution that we made. And that leaves us with the integral of u du over negative 5. I can write this as the integral with negative 1/5 on the outside of u du. So now that we've made that variable change, our function inside of the integral is much simpler. And this is going to help us decide which integration rule we should use. Now in our integral we have u du, and when we have this we're going to use our power rule. The integral of, I should use the general power rule, u to a power du is u to the n plus 1 over n plus 1 plus c. This is the power rule, so anytime we have a variable to a power, we're going to follow that power rule for integrals. We have u to the first power, so we'll carry down that constant multiple of negative 1/5, and u to the first power becomes u to the second power. We add 1 to the power, and we're going to divide by that new power. So we're going to divide by 2 and then add our constant. So this gives us negative 1/10 u squared plus c. Okay, we have one more step to do, and once we have found the antiderivative, what we want to do is change back to the original variable. We have u squared here, so this gives negative 1/10 cosine of 5x squared plus c. So we found that the integral of sine 5x cosine 5x dx is negative 1/10 cosine squared of 5x plus c. I had a student reach out about this problem, and the answer displayed is the one that we see here. But the student wondered why the answer had cosine when we could have chosen u to be sine. Remember I mentioned that one of the suggestions for choosing what u is to choose something that has a derivative in the expression. So how about we choose u to be sine instead? The derivative of sine is cosine, so that might work out as well. So let's give that a try. So this time I'm going to choose u to be sine of 5x. I'm going to calculate the derivative of sine. The derivative of sine is cosine. We're chaining. We're going to use the chain rule, leave the inside alone, and chain by multiplying by the derivative of the inside, which is 5. I'll go ahead and rearrange this. Du is 5 cosine of 5x dx, and dividing both sides by 5 cosine of 5x gives us dx equals du over 5 cosine of 5x dx. So we'll make this substitution for dx, and we'll make the substitution for u as well. So making the substitution would give us the integral of u cosine of 5x times du over 5 cosine of 5x. And I just noticed I have an extra dx here that shouldn't be there. We divided both sides by all of this, so the dx stays on that side. Okay. So making my substitution, I have u cosine of 5x du over 5 cosine of 5x. Just like in the last time we did this, our other variable cancels out cosine of 5x, which is a very good sign for us. We can write this as 1/5 the integral of u du. And again, we're going to use our power rule here to find the antiderivative. And that power rule states that we're going to add 1 to the power and divide by that power, and of course add our plus c. So this time we get 1/10 u squared plus c, which is bringing back our original substitution, 1/10 sine squared of 5x plus c. Now you can see that this is a different answer than we got before. The previous time we did this with the different substitution, we got negative 1/10 cosine of 5x plus cosine squared of 5x plus c. So clearly these answers are different. But one thing to keep in mind is that when you have trig functions, we have lots of identities and equivalencies between them. For this particular case, keep in mind the Pythagorean identity, sine squared x plus cosine squared x is equal to 1. And you can see that we have this plus c here, which can compensate for that 1. And so with this trig identity, these two could be equivalent, or are equivalent antiderivatives that we came up with. For this problem, we want to solve the differential equation. We're going to use C for the constant of integration. The differential equation we have is dy dx equals x minus 6 over square root of x squared minus 12x plus 9. So in order to solve this differential equation, we want to figure out what y is. So what I'm going to do is separate the variables by multiplying by dx on both sides. So that gives dy equals x minus 6 over square root of x squared minus 12x plus 9. So what I mean by separating the variables is having the y's on one side and the x's on the other side. And now I'm going to integrate the left-hand side and integrate the right-hand side. And on the left-hand side, the integral of dy, or just 1 dy, will be y. The antiderivative of 1 is y, which is exactly what we want. We want to solve the differential equation, which is to find y. And then on the right-hand side, a much more complicated integral to work out. So let's take a minute to look at this. I'm going to try to solve this with substitution. And one of the suggested substitutions is to choose something that is inside a radical in the denominator of a fraction or inside something in general. So I see that I have inside this radical x squared minus 12x plus 9. And we're trying to choose something that has the derivative there. And so I've got an x squared. The derivative of x squared is going to be 2x. And you can see that I have an x here. So this might work because I might have the derivative of what I'm choosing. So I'm choosing u to be x squared. X squared minus 12x plus 9. Then I'll calculate the derivative. The derivative of u with respect to x is 2x minus 12. Now you can see that this is not exactly the same as what I have in the numerator, but if I factor that 2, I have that x minus 6. So the only thing that I'm missing from this problem is a 2. So what I can do is I can multiply by 2 over 2. 2 over 2 is the same as 1, and multiplying by 1 doesn't change a problem. 1 times 5 is still 5. So I was missing that 2, but I'm going to resolve that by multiplying by a form of 1. Okay, so now I'll bring in the 2, and this is going to be y equals 1/2 the integral of x minus, when I multiply by that 2, it becomes 2x minus 12 over the square root of x squared minus 12x plus 9 dx. So now I've got it in the proper format for this to work. Going back up here for a second, I'm going to fully substitute this. Right now, I've got it written in sort of a pattern recognition format where we could calculate the integral as it is, but I think it'll be a lot more clear which antiderivative rule we should apply if we fully substitute. So we're going to substitute this for u, and then I'll make a substitution for the dx as well. So we're going to multiply both sides by dx. That gives du equals 2 times x minus 6 dx. I'll divide both sides by 2 times x minus 6. And that gives that dx is equal to du. Let's multiply that out, 2x minus 12. All right, so we'll make this substitution here. This gives y equals 1/2 the integral of 2x minus 12 over the square root of u times du over 2x minus 12. This cancels out the 2x minus 12. And I have y equals 1/2. I'm going to go ahead and rewrite the square root of u as u to the negative 1/2. Square root is the same thing as 1/2, and it was in the denominator, so I'm moving it to the numerator. So now that I've made that substitution, it's very clear which antiderivative rule I should use. That's the power rule. So the power rule looks like this. The integral of u to a power du is u to the n plus 1. So we add 1 to that power, divide by that new power, and we add our constant of integration. We have y equals 1/2 times we have the negative 1/2 power, so negative 1/2 plus 1 over negative 1/2 plus 1 plus c. This is y equals 1/2 times u. Negative 1/2 plus 1 is 1/2 over 1/2 plus c. I'll multiply by the reciprocal. So that's 1/2 times 2 over 1, u to the 1/2 plus c. That 1/2 and 2 cancel each other out, and we have u to the 1/2 plus c. The last thing I'm going to do here is bring back my original substitution for u. So this will give x squared minus 12x plus 9 to the 1/2 power plus c. So we've solved our differential equation. Y is equal to the square root of x squared minus 12x plus 9 plus c. Here I have an example of an indefinite integral. I have the integral of the square root, this is the 7th root of tangent 3x times secant squared 3x dx. I'm going to solve this with substitution, and I'm going to let u be inside of this radical. And I'm doing that because it's generally suggested that you choose something that's inside, but you also want to look for something where you have the derivative. The derivative of tangent is secant squared. So the derivative of tangent 3x is secant squared 3x times 3. So we have that derivative right there, the secant squared 3x. So this is a good substitution to make. So let me rearrange. Solving for dx, I have du equals secant squared of 3x. We put the 3 in the front and then multiply by the dx. I'll divide both sides by 3 secant squared of 3x. And we now have our dx being du over 3 secant squared of 3x. So we're going to make our substitution for u and make our substitution for dx as well. And this will give the integral of the 7th root of u, secant squared of 3x, and dx is du over 3 secant squared of 3x. The secant squared of 3x cancels, and I'll have 1/3 the integral. The 7th root of u I'll write as u to the 1/7 du. And now I'm going to use the power rule to find the antiderivative. So we add 1 to the power, 1/7 plus 1, and divide by that new power, 1/7 plus 1, plus our constant of integration. So this gives 1/3 u to the 8/7 over 8/7 plus c, multiplied by the reciprocal, giving us 7 over 24 u to the 8/7 plus c. And let's bring back our substitution. Our original u was tangent of 3x. This is 7/24 tangent of 3x to the 8/7 plus c. So we've solved that with u substitution. Okay, here we have an example of a limit. We want to evaluate the limit using L'Hopital's rule. Now, L'Hopital's rule states this. If we have the limit as x approaches c, f of x over g of x, and that equals some indeterminate form. Now, that indeterminate form could be 0 over 0, or infinity over infinity, maybe negative infinity over infinity, so some indeterminate form. Then we can rewrite this limit as the limit as x approaches c of f prime of x over g prime of x, and try calculating the limit again. So we have the limit as x approaches infinity of e to the 2x minus 7 over 3x. We're going to start with direct substitution, and that would give us e to the 2 times infinity minus 7 over 3 times infinity. So simplifying these essentially is looking at the graph of e to the x and 3x. If we look at the graph of e to the x, it looks like this. So as your x approaches infinity, your y is also approaching infinity. So here's our x approaching infinity, our y will approach infinity. Now then in the denominator we have 3x. The graph of 3x is a straight line. And as x approaches infinity, my y is approaching infinity. So that gives us our indeterminate form of infinity over infinity. So to apply L'Hopital's rule, we're going to calculate the derivative of the numerator, and that would be e to the 2x minus 7 times the derivative of the exponent. The derivative of 2x minus 7 is 2. And then derivative of 3x is 3. So now when we apply the limit again, we get e to the 2 times infinity minus 7 times 2 over 3. So the numerator is very similar to the original function and will approach infinity, but now we don't have infinity in the denominator anymore. We have a constant. Infinity divided by 3 is infinity. So we've solved that limit and it's infinity. Thank you for checking out my videos. Have a great day.